Hello, everyone. Thanks for joining us. I want to start off by thanking John Snow Labs and the organizers for putting together this fantastic summit and for giving me the opportunity to present my work today. In today's presentation, I will be diving into the key findings from a paper my colleagues and I recently published. The title of this paper is that LLMs will always hallucinate and we need to live with this. Throughout this presentation, I'll break down the very nature of hallucinations in language models, exploring why they happen, and discuss why we may need to accept them as an intrinsic part of working with AI. I'll start by walking you through the mechanics of LLMs, the different types of hallucinations we encounter, and the mitigation strategies currently in use. While a lot of these strategies have value, I will explain why we can't fully resolve the issue of hallucinations just by addressing just by working with these strategies. I will also introduce the concept of structural hallucinations and explain the mathematical and logical principles that make them inevitable. By the end of this talk, I hope to challenge the prevailing belief that LLM hallucinations can be completely eliminated, and I hope to offer a new perspective on how we might adapt to them instead of just trying to eradicate them entirely. Before I start, here's a link to the paper. So the paper is available on ArchiveX, and you could just scan this link to follow along and reference the details as we progress through the talk. While I'll cover the key points through this presentation, the paper here will provide a much more in-depth analysis and it will also walk you through all the mathematical proofs. And this is for those who are interested in exploring this beyond the talk that we have today. A bit about myself. I currently head the data science team at United We Care. My work here focuses on the intersection of generative AI and mental health. Some of the key challenges I work with are causal reasoning in artificial systems, hallucination mitigations, specifically in language models, and solving the needle in the haystack retrieval problem for large information systems. And in our quest to solve these challenges, we've built a vertical large language model, which was specifically designed for the healthcare sector. We also developed a clinical knowledge graph which spans over 16 million nodes and 220 million relationships. And this encompasses, all the proteins, all the genes, all the drug-drug interactions, all the illnesses, and it's a very comprehensive graph which powers the spatiotemporal graph neural network that we fundamentally use for modeling causality. My team and I have also set about 23 world records in natural language inference, and we have about 4 world records in ASR. We were the first ones to build an ASR model for the open source domain. I've also filed about 12 patents, and I've authored over 10 research papers spanning the work that we've done in AI and mental health so far. So I want to briefly touch upon how language models work before we get into the meat of the proofs and the claims that we have as a part of this paper. At the core, language models are essentially token prediction machines. Essentially, what they do is take in a sequence of tokens, which could be either words or parts, and predict the next best token. Now, this process involves converting tokens into numerical embeddings, adding positional information, and using self attention mechanisms to understand relationships between these tokens. And most of the current architectures and the techniques that they use revolve around using something like a absolute positional encoding, or something more advanced like rotational positional encoding, which is what transformers use to capture token positions. And then, they essentially have the self attention mechanism, which helps the model determine which parts of the input are relevant for predicting the next best token. This process essentially repeats, allowing the model to generate coherent text, which we use as humans. Now, as these models scale over time, we observe behaviors which are apparently intelligent. However, it's important to understand that language models can't think or reason, and they don't have a concept of truth. All they do is mimic human like text based on the statistical patterns that they learn in their training data. This fundamental nature of being pattern matching and prediction engines rather than reasoning systems is key to understanding why LLMs sometimes produce what we call hallucinations or false information. Through our research, we've identified four types of hallucinations. First one is factual incorrectness. So this is when the model just gets plain facts wrong. For example, it might just incorrectly state the date for any historical event, or if you ask, say, if you ask for the capital of Canada, the model might just return the city Toronto instead of Ottawa, and this is because the words Canada and Toronto are more often mentioned together, making it likely for the model to select Toronto as the answer rather than Ottawa. So far, I think there has been sufficient demonstration of the fact that LLMs have been known to give incorrect answers to logical and mathematical questions with a high degree of confidence. So that's the first one, which is factual incorrectness. Second, we have fabrications, which is a bit more severe. Here, the model generates entirely false information that has no bias even in its training data. It is essentially creating friction and presenting that friction as fact. Um, just as an example, language models have generated entire judgments which were fabricated, or they've misattributed legal cases, and these have had serious consequences for people who have trusted these models with such important decisions. Third, we have the needle in the haystack problem, which essentially manifests in two ways. Either there could be a missed key data point, or the model could just be partially correct. Where the model has missed a key data point, there it normally tends to provide incomplete information, and it might just omit some crucial details about the generation. So, for example, if you ask the model about World War I, it might just mention about the assassination of Duke Ferdinand without referencing broader context of alliances, militarism, and nationalism, which will lead to an incomplete understanding of the topic, but the information itself provided is not incorrect. Another way of incorrectness is partial incorrectness, where the model has mixed accurate facts with errors, creating a blend of truth and falsehood. For example, the model might state that Neil Armstrong was the first man to walk on the moon in 1959. This is partially correct because Neil Armstrong was the first man to walk on the moon, but he did so in 1969 and not 1959. And finally, we have misinterpretations, which also come in two forms. The first one could be a misinterpreted corpus, where there could be ambiguity of context within the training corpus. For example, a model might misattribute the signs of anxiety to depression, which has many overlapping symptoms and may often be used as a synonym for anxiety in a lot of colloquial texts. Then you also have misinterpreted prompt, where because of ambiguity in the user's wordings, grammatical errors, or misinterpretation of the instructions that the model receives, it might just produce a lot of fabrication. So a good example here would be when if you ask a model to translate a question, or if you just give it a specific instruction, it might just do something completely different, or it might just reply to the question rather than translating it. It's important to note and understand that hallucinations in language models can occur even with the best of the training, with fine tuning, or with the use of techniques like chain of thought prompting or retrieval augmented generation. In our research, we identified five key stages of any language model operations. These stages are training, intent classification, information retrieval, output generation, and post generation fact checking. And what we've noted is most of the work that has been done on the mitigation of hallucinations in the research domain has been done on either one of these five stages. And these could be, coming out. If I talk about the training stage, it could be something like people have explored different models like CANs, Mamba. People have looked at fine tuning techniques like LoRa, PEFT, just all of these. If you talk about intent classification and information retrieval, there has been significant amount of research that has been done on improving the chain of thought prompting, and also improving retrieval strategies from any external vector database that the data might be stored in. In the output generation phase, people have looked at self consistency techniques to kind of validate and verify the information that has been generated by the language model, just to see whether the generated text is coherent and factually correct. And then we have post generation fact checking, where you have one language model which is ideally um, either the same language model is verifying its own output, or there are other mechanisms that are being used to check whether the language model has correctly generated the text that it generated. However, the fact is that hallucinations are not bugs. In our research, we focused on what we call structural hallucinations in language models. Now, these are inherent to every LLM architecture and training paradigm, and they are essentially unavoidable. Structural hallucinations have a non-zero probability of occurring and persist regardless of improvements in model size, training data, or optimization algorithms. Essentially, structural hallucinations are fundamental limitations which are baked into the very fabric of how language model generations work. It's important to note that there is another type of hallucinations that we actually did not talk about when we wrote the paper. And this type of hallucination is the algorithmic part of hallucinations. Now, these are the reducible components of hallucinations in language models. Algorithmic hallucinations can potentially be mitigated either through better training data, or through improved optimization techniques, or through enhanced inference algorithms. Most of the work that we just saw, which is the work that has been done to address hallucinations across these five stages, such as chain of thought prompting and retrieval augmented generation, primarily has been done to address this type of hallucination, which is the algorithmic part of the hallucination that we refer to. And the extent of algorithmic hallucinations can actually vary, and it might be different with different model sizes, with the training time that has gone into some of these models, and any of the other hyperparameters that were used at the time of model training. For our research, we specifically chose to focus on structural hallucination because while significant progress has been made in reducing algorithmic hallucinations, the persistent nature of errors in language models pointed to something that was far more deeper and structural, and that was the area that we wanted to investigate when we were writing this paper. Understanding these structural hallucinations was important for us in terms of informing the community about setting realistic expectations about language model performances, and for guiding future research efforts. To address the structural part of hallucinations, we took a very comprehensive approach by examining each stage of the LLM processing. Our key assertion is that hallucinations are inevitable at every step, and we've proven this using fundamental theories in computer science and mathematics. If we just take a walk through these stages again, these stages are training, intent classification, information retrieval, output generation, and post generation fact checking. And at each of these stages, we argue that, for example, at the training stage, we argue that the training data is inherently incomplete. And no matter how vast our data set is, or how vast the knowledge base is, it can never encompass all possible knowledge or context. At intent classification, we've shown that due to the complex and often ambiguous nature of language, accurate accurately classifying any intent for accurately classifying an intent for any query is undecidable. At information retrieval, we prove that accurate information retrieval is undecidable. So even if the information exists within the model's training base, retrieving it with 100% accuracy is sort of undecidable. At output generation, we demonstrate that hallucinations are inevitable during the generation process in itself. And post generation fact checking, we show that even fact checking mechanisms cannot fully mitigate hallucinations in language models. And to prove these assertions, we've relied on two major theories. First is Gödel's incompleteness theorem, which reveals that some truths cannot be proven within certain mathematical systems, suggesting limits to what can be definitively known. Second is the halting problem, which was introduced by Alan Turing. And the halting problem essentially asks whether a program will ever stop or run given a certain input, and it's proven to be unsolvable for all known cases. And this essentially highlights the fundamental unpredictability in computing processes. We've also referred quite a bit to the acceptance problem, which deals with whether a Turing machine will accept a specific input. And like the halting problem, it is undecidable, meaning we can't always predict a machine's output based on its programming and inputs. In the context of large language models, these concepts will help us illustrate why we can't create a model that perfectly understands or generates completely accurate responses. Each stage of an LLM's processing, right from interpreting the input to retrieving the information and generating responses, can encounter situations where the model can hallucinate or generate plausible but incorrect information. I want to spend a little bit of time talking about the proofs, where we start with Gödel, then turn to the halting problem, and finally we draw on from the acceptance problem to show the inherent undecidability in language models. If I talk about the fact that no data set in its entirety can ever be fully complete, and Gödel's incompleteness theorem beautifully illustrates this point, showing that in any sufficiently complex systems, there are always truths that can't be proven, or that in the case of language models, there are facts that can't be known or learned from the data that they're trained on. Now, imagine we had a data set that we thought contained every fact about the world. According to Gödel's incompleteness theorem, there will always be true statements, facts about the world, which are not included in this data set, no matter how comprehensive it is. Since language models learn and generate outputs based solely on the data that they're trained on, this incompleteness will sometimes means that they will sometimes hallucinate. That is, they will generate outputs that seem plausible but are actually incorrect or not based on factual data, simply because the model is filling gaps in the incomplete training data. The proof by contradiction used in Gödel's theorem can be paralleled in understanding language model outputs. No matter how hard we try to expand or enrich the training data, there will always be some aspect of the knowledge that remains unrepresented. This leads to outputs that cannot be verified or are outright errors, underlining the perpetual gap between what the LLM knows and what is true. To illustrate, I we can just take the example the we can just take the statement that is shown in the slide here, and the statement is, this statement is true and not provable. Now, this is a classical example of a self-referential paradox that Gödel used to illustrate his incompleteness theorem. If we claim that this statement is true, then, as it says, it cannot be proven within the system, pointing to its incompleteness. If we claim that it's false, then it must be provable, which leads to a contradiction, thus implying inconsistency. And this paradox is something that can essentially be modeled to highlight the limits of any formal system in capturing all truths. Next, we look at the halting problem. The halting problem basically tells us that it's impossible to create a universal algorithm that can predict whether any given program will eventually stop or keep running forever. So, how does this apply to language models? Just like a Turing machine can't predict its own halt, a language model cannot tell when it will stop spitting out words. And now this essentially means two things. A, that a language model cannot a priori know when it will stop generating or essentially it will halt. B, they cannot predict exactly what they're going to say next. Since language models work on probabilities and they're probably thinking about the generation along the lines of, based on what I've generated so far, this is the word that might come next. But without an endpoint in sight, they will probably keep generating something forever. And so they're capable of generating anything, which could also include Gödel like sentences such as, this statement is both true and false, or something like, the next statement is true, but the previous statement is false, or something like, I'm currently hallucinating, in this exact sentence. We now tackle another tricky part about language models, which is the needle in the haystack problem. Now, the needle in the haystack problem is something that sounds really simple. And essentially, essentially, the line of thought is if all the facts are there in the data set, then surely a language model should be able to pull out the right one when needed, right? Well, that's not really the case, and it's a lot harder than what it sounds like. Imagine you're trying to find one specific fact in a vast sea of data. This data set is enormous. Think of it as like an infinite stack where what we're looking for, which is the needle, could be any piece of information. The size of the data that we're dealing with is virtually limitless, and so the volume alone makes pinpointing the right information incredibly challenging. The needle could be any fact specified in countless ways, which just adds to the confusion. To get to the crux of why this is undecidable, we draw parallels with the acceptance problem, known for its undecidability within halting machines. Here's how we tie it back. Let's assume that the needle in the haystack problem is decidable, meaning language models could determine if they can correctly retrieve the needle every single time. If the needle in the haystack was truly decidable, then by extension we could solve the acceptance problem. We would essentially create a system that could predict whether a given input is the exact piece of information we are looking for every single time. However, since we know that the acceptance problem is undecidable, and if so, our assumption leads to a solution for an undecidable problem, our initial assumption must be incorrect. Next, we look at another layer of complexity that stems directly from the needle in the haystack challenge that we just discussed. Intent classification in language models can be thought of as trying to decipher the specific meaning or intent behind a user's input. It's like trying to understand not just the words spoken, but the thoughts and the context behind them. Now, while most humans have developed a knack for this kind of a contextual understanding, language models with their limited grasp of context can often misinterpret or misclassify intents. It's just like finding a specific fact in a vast data set is undecidable. So too is pinpointing the correct interpretation of a user's intent among a possible numerous possible number of meanings. For example, if you use the word lead, LEAD, that could mean the metal, or it could mean leadership. It could just mean an n number of things. And so the fact is that a user's input can be interpreted in many different ways depending on the context, making it difficult for the language model to identify the intended meaning accurately. And therefore, LLMs, given the multitude of ways language can be used and understood, there is always a non-zero chance that a language model will misconstrue the intent behind any given statement. If intent classification were decidable, that would imply that a solution to the undecidable needle in the haystack problem is exists, which is something that we've established is already undecidable. And finally, we turn to the fact checking process. Now that we've established that language models cannot always retrieve accurate information or guarantee that their outputs won't be hallucinatory, uh, most of you might wonder why can't we just fact check against a reliable database. However, the fact is that no matter how comprehensive a fact checking system might be, it cannot be exhaustive, and it has the same challenges from our incomplete data set that we established in the first proof, which was regarding Gödel's incompleteness. The process of verifying every piece of information in a language model output against known facts is bound by the finite nature of these systems and the infinite potential for variations in data. Now, suppose we assume an ideal scenario where an LLM can generate the perfect response for any given prompt, and we compare this output with the ideal language model using a Turing machine, which is designed to modify and fact check these outputs. Uh, uh, if we assume that it's possible to modify any LLM output to match uh, the ideal output through finite series of corrections, and if we were able to establish that this was true, then we would construct then we would end up constructing a decision procedure for the undecidable acceptance problems, which is determining whether a Turing machine will accept a certain input. And if we can modify an LLM's output to match with the ideal number of finite steps, we would have effectively solved the acceptance problem, which is known to be undecidable in language models. Now, since this is a direct contradiction, this might imply that our assumption about the finite effective fact checking must be false. And I understand that while a lot of this proof would be is a lot of there's a lot of information here. We've covered a lot of ground, so I just quickly want to recap the assertions that we made. First, that no training database can be 100% complete. Second, even if the database was complete, LLMs will not be able to retrieve information with 100% accuracy. Third, that language models will not be able to classify any intent with 100% accuracy. Fourth, that no a priori training can completely eliminate hallucinations. And five, no amount of fact checking can completely eliminate hallucinations. I want to illustrate a few examples through which we can show that language models will always hallucinate. This is the most famous strawberry problem, which I think was noted in ChatGPT quite recently. If you asked it to correctly tell you the number of R's in strawberry, it would sometimes end up saying one or two or three, and then it would just keep cross guessing its own generation. Here are some of the prompts that we played around with when we were testing models for structural hallucination. At the age of 9, my height was 4. At the age of 10, it was 5. And then we gave it a logical sequence. And what we did is we broke the chain of thought and we said, at the age of 1000, what will my height be? You have to answer that in one line. And it said, at the age of 1000, your height will be 997 feet, which is kind of impossible to have. Another question that we asked, I'm sorry if it is slightly not visible, but in which year did Netaji Subhash Chandra Bose resign from Congress in the presence of Socrates? And then we gave it four options, among which was none of the above. Now, Socrates and Subhash Chandra Bose existed in two completely different eras, and just because we broke the chain of thought, the language model ended up saying that this event happened in 1939. And when we asked it to analyze this in detail and check whether it had generated the answer correctly, it gave us a whole line of reasoning to explain why the generation was correct when in fact it was not. Um, just another example, we asked which among the following did Shakespeare write in the context of Shakespeare's landing on the moon, which we know is factually incorrect and kind of never happened. But the LLM still answered to be or not to be. That's because there is no concept of reasoning in language models. They just know, based on the training data, what would be the right prediction or what would be the right output. Um, this is an example from a model that was launched very recently, which is GPT 401, which I think is the strawberry model, which relies a lot on chain of thought for responding. And I was trying to, test it by generating some proofs. And I said, give me a very short reply of how did you verify the proof before writing, and that you can also say that you have not verified if you did not verify it. And after thinking for 6 seconds, the language model said, I did not verify the proof before writing it. Now, this just goes on to illustrate that no matter how much we try, and no matter how hard we train language models, no matter how much of chain of thought prompting we give, we still cannot teach these models how to reason, because that's something that they will fundamentally never be able to do. And this is where structural hallucinations will always stay and continue to remain so. Finally, I think the question that everybody's been asking is who pays for the errors and the misinformations these systems might propagate. because there's a stark disparity in how accountability is distributed across different professions. In healthcare, a doctor can face strict liability for the errors that could harm their patients. And if a doctor is relying on a language model for their decision making, it is the doctor who will be held accountable if the language model is wrong, and not the engineer that developed these language models. The fact is that language models can generate and amplify information and disinformation at a scale and speed that is far beyond human capabilities. Many users also attribute a level of authority or accuracy to AI generated content that exceeds their skepticism of human generated content. We all agree that this is, in fact, quite dangerous. However, while I've spent a lot of time talking about the fact that LLMs will always hallucinate and that these hallucinations could be dangerous, I would like to iterate that I truly believe in the power of language models and AI in general. While we've outlined the risks and the potential negative impacts of hallucinations in language models, it's important to remember the immense positive potential they carry. Um, the fact is that we will have to learn to live with hallucinations. We will have to embrace them as inevitable. We will have to take steps to develop awareness and ensure that people who work with these language models or use them for their work are sufficiently cautioned about any claims that are made to completely remove hallucinations, because that would ideally never be the case. And it's also important to incorporate human insight as a part of the whole process, where there should be a human uh, who uh, who has the sufficient skill set to verify and accurately gauge the information that a language model has generated. In our future work, we will continue to focus on structural improvements of language models to better understand and mitigate these hallucinations. We will focus on systemic studies for identifying and reducing hallucinations, and for developing targeted benchmarks to measure the improvements that models make in terms of removing hallucinations accurately. We will also look at domain specific mitigation strategies, increasing AI literacy, and strengthening safety measures for vulnerable users who will be exposed to language models. I want to thank you all for your time, and I hope you enjoyed all the sessions today.
This concludes today's conference. I would like to extend my appreciation to the speakers for their comprehensive discussions on putting generative AI to work in healthcare and life science. We have seen firsthand the potential of this technology as well as the challenges, from precision oncology and drug discovery to cancer detection and improving hospital operations. We will continue tomorrow at noon Eastern Time for the third day of this fifth NLP Summit. We will talk about putting generative AI to work in finance. Enjoy the rest of your day, and see you all tomorrow.